Hello everybody. This is Matteo Camilli here, and well, I'm supposed to deliver to you this virtual presentation about this piece of work, this contribution that has been accepted at the first workshop on model-driven engineering for software architecture. And yeah, this is entitled Continuous Formal Verification of Microservice-based Process Flows. And okay, so I'll try to give it to you later on, comprehensive overview on what's going on under the hood of these ongoing research project, and then later on during the live question and answer session, I'll be happy to reply your questions to go more into the details if you want, if you are curious enough. And okay, so by a way of introduction, my name is Matteo Camilli, and currently I'm a research fellow at the computer science faculty of the University of Bolzano, Italy. I currently work in the software and system engineering research group, and my research interests cover the macro areas of software engineering and formal methods. And yeah, here you can also find my email address if you want, and also a link to my personal webpage. Okay, so outline. I'm gonna spend a little bit of time discussing, introducing this work, discussing motivation and objectives. I'm gonna talk to you about the microservice architectural style and the DevOps setting, and I'm gonna introduce the idea of continuous formal verification in a DevOps setting, and then I'm gonna spend the majority of the time introducing at least the ideas onto these formal verification approach that mixes design time and runtime verification integrated into a DevOps loop. And yeah, and then in the end, we'll try to draw a conclusion. Okay, so let's get started with the introduction. So I'm not going to spend that much time here because I'm pretty much sure that you already know, you are already familiar with the notion of microservice architectural style. So it's basically an architectural style inspired by service-oriented architecture. And but we can basically find the roots of these design principles inside Unix, which is basically a highly component-oriented architecture with many small specialized black box pieces of functionality combined together by means of the glue of the shell. And if we apply microservices in a good way, these eventually lead to huge benefit like modularity, maintainability, scalability, and so on and so forth. And I'm not going to spend time discussing these, benefits. So the point is basically that microservice is a sensitive matter nowadays. So many companies are adopting microservices or are moving towards these architectural style. Here we have leading examples like Netflix, Amazon, Uber, and so on and so forth. And companies that are adopting this architectural style often work in these setting, these DevOps setting. You can see the schema of DevOps, the high-level schema of DevOps below at the bottom of the slide. And this basically, it is a setting that fosters tight collaboration between developers and operators. So we have these continuous and rapid feedback between the two phases from developers to operators and also the other way around. So the point is that these context favors, encourages rapid and evolving continuous modification of artifacts. So basically, on the one hand, it's very easy to change modules and their composition in order to define the system as a whole. But on the other one hand, it's very hard to ensure that these continuous changes achieve the desired goals in terms of requirement satisfaction, but more in general, functional and non-functional quality attributes of the final product that we deliver to final users. So basically, our approach here is to introduce this kind of continuous verification approach that should fit into modern agile development practices, um, covering basically both design time stages and runtime stages of the development process by emphasizing these, fitting boundary between these two phases, design time verification and runtime verification. So to basically to study the applicability of these formal verification approach, we confine ourselves into this context. So we basically leverage the experience of Netflix, and we target microservice-based process flow developed by means of the Conductor orchestration engine, which is basically an open source software developed by Netflix, and it is also in use by Netflix in its own production environment. So the schema that you can see here in this slide is basically an high-level overview on the whole approach. As you can see, there are two main phases. First one on the left is the model transformation and model checking that is intended to be applied during the development, in particular during the plan phase of the DevOps loop. And the second one on the right is the monitoring and runtime verification, which should be applied after the deployment stage, either during the testing phases or in production. So the starting point of the whole process is the description of the process flow by using the conductor domain-specific language, which basically contains a description of the microservice-based process flow by using building blocks similar to those that we can find in activity diagrams. And the point is that this kind of description does not have formal semantics. So we provide the formal semantics here in terms of time-based Petronet. So we develop these techniques, model-to-model transformation technique implemented inside these box, so-called blueprint compiler, that takes as input a conductor blueprint and produces as output a time-basic Petronet, which is basically this is our modeling formalism choice. Time-based Petronet, which is a timed extension of Petronet. So this is a very convenient formalism for describing distributed systems with time constraints. And once we have these, formal description of the process flow, we can apply model checking techniques. By means of a model checker, we can verify, for instance, formal requirements expressed, for instance, by using time computation tree logic, as represented here inside the red box. So if requirements are satisfied, we can then build the system and deploy it inside the testing, either the testing or the production environment, where we can basically continuously monitor the application by means of the monitor module that you can see inside the blue box. And the monitor module basically receives as input events coming from an instrumented version of the Netflix Conductor orchestrator. And the monitor builds a timed trace of events that are checked against the formal specification by means of a conformance game approach. And so the idea is to leverage this approach either during the load testing with expected workload condition to understand whether the system works as expected in the sense of the formal specification, of course, or during the production. So during the production phases, we can, continuously monitor the system with respect to the formal specification and provide fast feedback to developers in case of anomalous behavior or anomalous, environment conditions. So the continuous monitoring and verification provides feedback to developers that can use these information to change the blueprint, and we basically automatically reflect these changes to the formal specification and so on and so forth. And we continue following the DevOps loop. Okay, so to conclude, let me just recap a bit the important points of these work, and then later on, if you want, we can explore a bit more the details during the question and answer session. So basically, the measure aim is, of course, supporting the integration of formal methods inside modern agile practices. And in order to achieve these high-level goal, we try to integrate model-to-model transformation techniques, model checking, and runtime verification inside our methodology. And we try to fit, let's say, this methodology inside the phases of the DevOps loop. So we leverage solid foundation from well-established farm methods. So we leverage time-based patternets for the description of the microservice-based process flow. We leverage also time computation tree logic model checking and a conformance game approach to implement the runtime verification technique. So the current state of the work is as follows. So we basically study the applicability of the methodology by applying it on a simple taxing highlighting application. You can find the details of both the application and also the requirements that we verify at design time and runtime in the paper if you want. And we provided also a full formal semantics in the sense that all the building blocks that you can use inside the conductor domain specific language have corresponding transformation into time-basic patternets. So we have tool support for both the design time stages and runtime verification stages, and we delivered these two tools, Conductor 2PN and the runtime verification modules. These are open source tool to encourage the adoption, and of course, if you want, you can also contribute. They are open source projects. And okay, so to recap a bit the advantages of the whole methodology, so we try to deal with continuously changing specifications by keeping automatically up to date the formal specification by means of these model-to-model transformation. And the runtime verification technique can support both system testing activities when applied inside the the testing environment, and we can also support in production monitoring. So after the deployment of a release build in production, we can continuously monitor the application. Yeah, that's it, more or less. And yeah, of course, there are a lot of details that I didn't mention because of the small amount of time. But of course, if you have questions, I'll be happy to try to reply if I can. So thank you very much for your attention.